The LIGO experiment. So, as you know, LIGO stands for Laser Interferometry Gravitational Wave Observation. So this was an important experiment which historically detected gravitational waves for the first time in September 2015. It uses a pair of highly sensitive Michelson interferometers. These have arms that are capital L equals 4 kilometers long and use powerful neodymium YAG lasers with wavelength lambda equals 1064 nanometers. The beams traverse the arms both ways n is equal to 280 times before recombining, which effectively lengthens the arm length to L prime equals 1120 kilometers. The devices are tuned so that the beams destructively interfere when they recombine if no gravitational wave is present. Part A. The beam has a power of P is equal to 100 kilowatts concentrated into an area of a square centimeter. Calculate the amplitude of the electric field in the beam. Okay, so this is the part we will deal with for this video. Now, we have L given to us, the length of the arms, 4 kilometers. Wavelength is 1064 nanometers. They traverse 280 times. L prime is 1120 kilometers. It's tuned for destructive interference. We know permeability of free space is 4 pi 10 to minus 7 Henry per meter, and we know epsilon 0 permittivity of free space is 8.85 10 to minus 12 farads per meter. The power is 100 kilowatts, area is 1 centimeter square. We want to know the electric field amplitude. Now, remember that the intensity of an electromagnetic wave I is equal to the power per area, which is actually the time averaged power per area, but that's implied. So this is equal to the average value of the magnitude of the Poynting vector, which is the average value of 1 over mu 0 magnitude of the average value of electric field cross product with magnetic field. And we also know that between the magnitudes of the electric field and magnetic field components of an electromagnetic wave, we have a relationship E is equal to BC. So for B, we can substitute E over C, and at the same time, they're perpendicular to each other. So we can write this as 1 over mu 0 average value of the electric field amplitude, electric field squared, divided by the speed of light c. Why? Because we know that when the electromagnetic field propagates, the electric field component is magnetic field component times the speed of light. Now I want to recall, if the electric field at a given point in space is written as E max, the amplitude, times cosine omega t. So normally this is a traveling wave, but I'm fixing the position, so it's just time dependent at that position. If I look at the time average value of E square, this is going to be E max square. It's averaged over one period divided by the period integrated over one period 0 to t cosine square omega t dt. All right, so I know this. Now, if I continue with this calculation, what is the time average value of the electric field squared? It is E max squared divided by the period, integral over 1 period. Now for cosine square omega t, I'm going to write cosine 2 omega t plus 1 over 2. And then I have dt. Why? Because cosine 2 theta is 2 cosine square theta minus 1. So this is 2 cosine square omega t minus 1 plus 1 cancels. Divided by 2, I get cosine square omega t. Okay, now I'm ready to perform the integral. Just to remind myself what's the time average value of electric field squared. It is E max squared divided by 2 periods, 2t. Now, what's the integral of cosine 2 omega t dt? It is 1 over 2 omega sine 2 omega t, and the integral of dt is t. Remember that I've already taken this to the left-hand side, and this will be evaluated between time t equals to 0 and 1 period. All right, so if you substitute here cosine 2 omega period, since omega is 2 pi over the period, you will get sine 4 pi, which is 0. So, and sine 0 is already 0. So we can say that this term is going to give us 0. All right. And then we're left with the t period for this part, and t on this side and on this side will cancel, and I will have my answer, amplitude of the electric field squared, E max squared over 2. Okay, so going back to my intensity expression here, 1 over mu 0 c, time average value of the electric field squared. So I can remind myself that the intensity is 1 over mu 0 c E max squared over 2. All right. And if I multiply top and bottom with c, so let's do that here, multiply top and bottom with c, I will get c square at the bottom. So this will be c times E max square. C is the speed of light. And then at the bottom I have 2 mu 0 c square, but c square is 1 over mu 0 epsilon 0. The mu zeros will cancel, and I will obtain 1 over 2 c epsilon 0 E max squared, which is nothing but the energy density stored in the electric field multiplied by the speed of light. So c times the energy density, and that's equal to time average power per area. Okay, so you can see that I can calculate the amplitude of the electric field component from this expression. E max squared is equal to 2p over c epsilon 0 a, or in other words, I can write the electric field magnitude E max to be 2p divided by c epsilon 0 times the given area. All right. Now, if I plug in the numbers, E max is equal to Now, how much is the power? It is 100 kilowatts. So it's going to be 2 times 100 times 10 to 3 watts. Speed of light is 3 times 10 to 8 meters per second. Epsilon 0 is 8.85 10 to minus 12. It was given here, farads per meter. And this is for 1 centimeter square, 1 10 to minus 4 meters square. And then I have to take the square root of this in order to get my final answer. And therefore, I obtain my Emax to be 870 kilovolts per meter. So that's my answer to part A of this problem. So what have I done here? I've used the intensity power relationship. Intensity is the average power per area, which is the average value of the magnitude of the Poynting vector. Poynting vector is 1 over mu 0 E cross B. So I'm looking at the time average value of E cross B, and recall that E is equal to BC. So it is 1 over mu 0 C average value of E square. At a given point in space, E is E max cosine omega t. Its time average value is found by integrating E square over one period and divided by the period. And this gives me E max squared over 2. So I substitute E max squared over 2 for average value of E square, which gives me 1 over mu 0 C E max squared over 2. I multiply top and bottom with C, and then I recall that C is the speed of light is related to mu 0 and epsilon 0. It is 1 over mu 0 epsilon 0 square root. So I use this relationship here, and then I remember that the intensity is the energy density in the electric field component, stored in the electric field component, multiplied by the speed of light, and that's power, average power per area. And from this relationship, I can get Emax as 2p over c epsilon 0 a inside the square root. So that's the answer. And if I substitute the numbers here, 100 kilowatts, 3 times 10 to 8 meters per second, 8.85 10 to minus 12 farads per meter, and area is 10 to minus 4 meters square. It was 1 centimeter square. We obtain our final answer, 870 kilovolts per meter.